Good afternoon, children. Today I am going to teach you a new chapter on force and pressure. What is a force? A force is an external, which means outside cause, which changes the state of a body, either the state of rest or the state of motion, or changes the shape or size of a body. Example, we have a push or a pull, and if you look at this figure, you'll see one person is pushing and another person is pulling, and here is a body. So these are forces that they apply upon a body. Now, a force is coming from outside, so we call it an external cause. Okay, it is not from inside. Now, when you apply a force on a body, it can change the state of a body. When we say the state, means a body at rest can go to motion, or the state of motion, that means a body in motion can come to a stop. Or it can change the size or the shape of the body. So these are the effects that we have whenever we apply a force. So the few examples here are a push, a pull, a squeeze, etc. Unit of force. The SI unit of force is Newton. Please remember to write it all with small letters, okay? The symbol for Newton is capital N. Definition of 1 Newton. 1 Newton is a force which, when acts on a body of mass 1 kilogram in the direction of its motion, increases its speed by 1 meter in 1 second. What does that mean? That means when we apply a force and the body has a mass of 1 kg, then when we apply a force in it, then this body will increase its speed by 1 meter in 1 second. Okay, so this is the SI unit of force. The force of gravity, or the weight of a body. It is the force with which the earth attracts a body towards itself. And this force is different at different places of the earth. Now, please remember, children, when we talk about the force of gravity, usually we refer to it from the side of the earth. But when we take it, the same force, when you take it from the side of a body, we call it the weight of the body. Hence, the force of gravity, or the weight of a body. All right. The force of gravity on a mass of 1 kg is called 1 kgf, or 1 kilogram force. The full form of kgf is 1 kilogram force. Now, 1 kilogram force is equal to 10 Newton. So it's a much higher force. It is 10 times that of a Newton. Whenever we apply a force upon a body, it depends upon a body whether it's free to move in straight line or whether a body is not free. If you think about a body which is pivoted at a point, then a body will not be free to move in straight line. If you think about a seesaw, it is pivoted at one point, so it will not move in a straight line when you apply a force to it. Instead, it will rotate up and down, okay? So a force has the turning effect upon a body. A force has a turning effect on a body which is not free to move in a straight line, but is pivoted at a point about which it can turn. This is important, remember. A body which is free to move will move in straight line, but a body which is not free to move, which is fixed at one point, we call it pivoted at one point, then it will simply move about in the form of rotation. That means it turns around about this point. Okay. The factors affecting the turning of a body. The turning effect of a force on a body depends on the following two factors. Number one, the magnitude of the force applied. That means how big the force is applied. Okay, how big is the force that is applied? Larger is the magnitude of the force, more is the turning effect of the body. That means bigger is the force, more will be the turning effect. Smaller is the force, less will be the turning effect on a body. The next factor is the perpendicular distance of the force from the pivoted point. Whenever we apply a force on a body which is pivoted at a point, we have to apply it at some distance. Okay, and here is the effect. Larger is the perpendicular distance of the point at which the force is applied. From the pivoted point, more is the turning effect. That means if a pivoted point is here, and then we take a large distance to apply the force, then more is the distance, more will be the turning effect. Here are a few examples. Okay, this is a spanner. It's pivoted at this point. Okay, and because we have a pivot here, then when we apply a force, we will not apply a force near the pivot. Instead, we will apply the force at a large distance as possible. Okay, then we will have the turning effect. Then it will turn. Okay, it will turn. So you will have the turning effect. Another example is a steering wheel. In a steering wheel, one hand will push it in one direction, the other hand will push it in one direction. So you will see on one hand you'll have one force here, on one hand you have another force here. As a result, the steering wheel will turn. Okay, and the pivoted point is here. So this is the pivoted point. Similarly, when you apply the force on the pedal of a bicycle, so the pivoted point is here, and the force that you apply on the pedal will be transferred through the chain to this point, okay, where the axle of the tire will be. So when you apply the force with your feet, one foot will make the force to move this side, and the other one will make the force to be on this side. As a result, you will find a chain will rotate in one particular direction. As a result, the tires will get the motion and they will move forward. So this is also an example of the turning effect of a force that we have. The next one is the one that you usually apply at home, knowingly or unknowingly. That is in opening and closing the door. In this case, we have the hinges as the pivoted point. And because we have 2-3 hinges here, so this will not simply be the pivoted point, but it will also be the axis of rotation since we have a huge body. Okay, so usually we apply the force near the edge of a door. We have the handle here, so the force will be applied here, and this point is at a point which is the highest distance from the axis of rotation where it is pivoted. Okay, so this is the perpendicular distance and here is the force. All right, so at a maximum distance. Why do we do so? Because we want to have maximum turning of the door to open it or to close it. The next example is in this body, okay? And if you look here, when you push it with this hand, you will find one force is moving this side, and with the other finger, you are pushing it in the opposite direction. As a result, you get the movement of this body, okay? So to get the maximum movement, the distance between your two fingers should be maximum, at a maximum distance from each other. Then only you get the turning effect to be large. Moment of a force. What is moment of a force? Moment of a force. From the above examples that we have seen, we see there are two things that we need to understand. We have the force and we also have the perpendicular distance from the pivoted point. So moment of a force is defined as the product of the magnitude of a force and the perpendicular distance of the force from the pivoted point. In other words, moment of a force is the measurement for the turning effect of a force. Okay, it's the measurement of the turning effect of a force. How do we measure the turning effect of a force? Is equal to the product of the magnitude of the force and the perpendicular distance of the force from the pivoted point. Okay, to be clear, let's consider this body. All right, this body which is shown here. Consider a body which is pivoted at O. So this is the pivoted point. Okay, this is the pivoted point. If a force is applied on a body in the direction FP, so here is a force that we apply, and then its direction is in the direction FP. It goes like this, all right, FP, as shown in the figure. Then the body is not able to produce linear motion in the direction of a force, all right? This body is not free to move in straight line. So it's not able to produce the motion in straight line. So the motion in straight line is known as the linear motion, but this body cannot move in a straight line because it is pivoted. Instead, it will move in the direction of FP. So it will move like this. Because the force is applied in this direction, so it will move in the direction of the force applied, okay? It will rotate about a point O in the direction as shown in the figure. So instead of moving in straight line, it will rotate like this. It will rotate, okay? So this is the direction of rotation. Now, here, force is F. So here is F, all right? And then the perpendicular distance of the force F from the pivoted point O is OP. The distance between F, here is the point where we apply F. So from here to O, the perpendicular distance is OP, all right? So the distance from where we apply the force at P, and the pivoted point is at O, so the perpendicular distance is OP. Hence, moment of force, according to this definition, the moment of force about O equals F into OP. Unit of moment of force. Unit of moment of force is equal to unit of force into unit of distance. What is moment of force? It's force into distance, okay? So in the unit of moment of force equals unit of force into unit of distance. Now, SI unit of force is Newton, SI unit of distance is meter, so SI unit of moment of force is Newton into meter, which we write in short Newton meter. And the CGS unit is dyne centimeter. Okay, because CGS unit of force is dyne, CGS unit of distance is centimeter, so CGS unit of moment of force is dyne centimeter, where 1 Newton meter is equal to 10 to the power 7 dyne centimeter. This is the relation between the two types of units. Now, if the force is measured in gravitational unit, that means the unit in force of gravity, then the units are kilogram force meter and gram force centimeter, where 1 kilogram force meter is equal to 9.8 Newton meter, and 1 gram force centimeter is equal to 980 dyne centimeter. Okay. Now, moment of force can be clockwise or anti-clockwise, which means moment of force has direction. Okay, and the direction can be clockwise or anti-clockwise. Look, when a body on the application of force moves in the clockwise direction is like this. So this body is moving in the clockwise direction. So we have clockwise moment. But in this case, a body is moving in this direction. Clockwise is like this, but this body is moving opposite to it. So we have anti-clockwise moment. Then we go to pressure. What is pressure? Before we go to pressure, we need to know one term which is related to it, that is thrust. A force acting normally on a surface is called thrust. Now, please remember, not all forces are called thrust. Only the force that acts normally. Okay, this word is very important here. What do we mean by the word normally? Normally means perpendicularly. So only a force which acts perpendicularly on a surface is called a thrust. Look at this force, okay? We have the force acting here, and here is the surface, and this force is acting normally or perpendicularly to the surface. So this is thrust, okay? Now, the effect of thrust depends upon the area of the surface it acts. Smaller is the area of the surface on which it acts, larger its effect. It means when a thrust is acting upon the area, if the area is small, then the effect of thrust will be more. If the area is large, the effect of thrust will be small. Then we go to the next, that is pressure. What is pressure? Pressure is defined as thrust per unit area. Alright, thrust per unit area. Whenever you have the word per unit, it means divided by. So here it means pressure equals thrust divided by area. Okay? Pressure is denoted by P, capital P, and thrust is a force, so it's denoted by force, okay, by F, and area by A. So symbolically, P is equal to F by A. Remember children, we hardly symbolize this by T, capital T, because capital T is used for time period. Instead, we write F, alright? Though we say it's thrust, but thrust is a force. So we write it by F divided by A. Then we go to unit of pressure. Now, unit of pressure will be unit of force divided by unit of area. So, SI unit of force is Newton, SI unit of area is meter square. Hence, we have the unit of pressure as Newton per meter square. And Newton per meter square has a specific name which is called Pascal. Write all small here also, Pascal. Okay, when you write in full, Pascal, all small. But the symbol is capital P and A. Alright, this is a symbol for Pascal. Definition of Pascal. 1 Pascal is the pressure exerted by a thrust of 1 Newton on a surface area 1 meter square. Remember, pressure is force by area. So 1 Pascal is a unit of pressure. So 1 Pascal is the pressure exerted by a thrust of 1 Newton on a surface area of 1 meter square. Not on 1 meter, it's area. So meter square. So we have 1 Pascal equals 1 Newton by 1 meter square. Or symbolically, 1 PA is equal to 1 Newton by 1 meter square. And anything that is written in the denominator, if you want to write it in a single line, then the power of the denominator will become negative. So we can write it as 1 Newton meter to the power minus 2. Okay. Then the bigger unit of Pascal is kilopascal. Symbol is kPa, where 1 kilopascal is equal to 1000 Pascal. That is 1 kilopascal is equal to 10 to the power 3 Pascal. Alright, you will be learning more of these metric multiples and submultiples in class 9. But just for you to have an idea, children, the word kilo means 1000 times. Okay, the word kilo means 1000 times. So whenever you have any quantity with the word kilo, it means 1000 of that quantity. So this is kilopascal. So we have 1000 Pascal. If it is kilogram, it means 1000 gram. Alright. And we can write this in short as 10 to the power 3, which means 1 with 3 zeros. Alright. So 10 to the power 3 Pascal. Now, if thrust is measured in terms of kgf and area in centimeter square, then pressure is expressed in a unit kgf centimeter to the power minus 2. Alright, we can express kgf along with centimeter. There is no fixed rule that we should change centimeter into meter. Alright, so we can write kgf centimeter to the power minus 2. And this is important. The atmospheric pressure is generally expressed in a unit of atmosphere. In short, we write it as ATM. Remember, children, this is not ATM machine. This is a short form for atmosphere. Okay, where 1 atmosphere is equal to 76 centimeter of mercury. All right, mercury column, because the atmospheric pressure is measured with the help of an apparatus called a barometer, and barometer is usually expressed in terms of mercury column. So 76 centimeter of mercury column, but remember its relation with Pascal. 1 atmosphere in terms of Pascal is equal to 1.013 into 10 to the power 5 Pascal. So 1 atmosphere is much higher than Pascal. The factors affecting the pressure. Now, whenever we come to the factors, remember the quantity. All right? If you remember, what is pressure? Pressure is force by area. So the factors on which the pressure depends will also be on those two. Number 1, on the area of the surface on which thrust acts. Smaller the surface area, more is the pressure exerted by the thrust, and larger the surface area, lesser is the pressure exerted by the same thrust. If you give the same thrust but area is different, on a small area, more thrust. On a large area, less thrust. Okay? Less pressure, because though the thrust is the same, but the pressure also depends much on the area. So it's very important to remember this factor. Then 2, on the magnitude of thrust acting on the surface. Greater the thrust on the surface, more is the pressure on it. While smaller the thrust on the same surface, less is the pressure on it. Okay? Now, let's have a look at some of these examples which I have given here. At the same time, these are also applications of reducing the area, more is the pressure. Alright, so you look at these heels, alright, they are very small if you compare with the blocks. Because the heels are small, the area of contact here will be small. So you have less area, okay? Less area of contact as compared to the block. So what will happen? You are giving much pressure to the ground whenever you walk with these heels. All right? Less area, more pressure. Okay? Less area, smaller the surface area, more is the pressure. So if you wear heels which are very small, like this, you reduce the area of contact, so that the pressure that you give to the ground will be more. Here are some cutting tools, okay? You'll find that in the cutting tools, one side will be blunt and one side will be sharp. The sharp side will be used for cutting, not the blunt side. And in all the cases, you will find the sharp side is the one that we use for cutting. Why is it so? Because when you have thin and sharp side, you reduce the area of contact to the body to be cut. Okay? So when you reduce the area, you can give more pressure to the body to be cut, because smaller the surface area, more is the pressure. That is the reason why we make all cutting materials, cutting tools to have small surface area, very thin at the point of contact with the material to be cut. Similarly, a nail, okay? A nail is different at the two ends. On one side, it will be bigger and then blunt. On the other side, it will be sharp and pointed. And when we want a body to be fixed, a nail to be fixed to a body, say a wooden plank, what do? The sharp pointed end will be made to face towards the plank. As a result, less area, small area is towards the plank. So this side will have more pressure, which makes the nail to be easier to get inside the plank. Whereas from this side, because it is flat and blunt, there is less pressure needed, but more pressure will go to this side. Okay, examples of increase. This should be increase in area decreases the pressure. Okay, increase in area of contact decreases the pressure. Okay, the first example that you see here is a truck. The conventional truck has only 4 tires. Okay, has only 4 tires. So you will have on the front 2 and then on the back 2. So only 4 tires. We have to remember, for a truck or any vehicle, the point of contact to the ground is only at the point where the tires come in contact with the ground. There's no other point where a truck will come in contact. Now, this area of contact, if there are only 4 tires, it will be very small, because you see a tire not at the same time it will touch the ground. Only the portion that comes in contact with the ground. So this point will be the area of contact, this point will be area of contact, this point will be area of contact. So there will be very small area of contact. When there is smaller area of contact, more will be the pressure. Okay, more will be the pressure. And where will the pressure of the truck, if there are only 4 tires, be? It will be on the tires. Hence the tires will puncture. Okay, will puncture because of the weight of the truck. Now, if we have more number of tires, okay, like in this case, we have 2 here, 2 here, so 4, and then these are 2. Okay, so 2 here, on the other side 2, so it will be 8. There are 2 here, 2 on the other side, so there are 12 tires altogether. With 12 tires, the area of contact is increasing considerably. So when area of contact is increasing, there will be less pressure on the tires. As a result, the tires will not puncture easily. Now, these are the feet of a camel. Okay, camel's feet. If you look at the camel's feet, they are very different from the feet of a cow or a goat. All right, you will see the feet of a camel are broad. Okay, moreover, they are soft on the inside. They are not as hard as the hooves of a cow. So, because they are broad and soft, all right, so what happened? They will have more area of contact. And because they are soft, they are not hard, so the pressure that will be given on the sand will be reduced. Okay, area of contact is already increased and they are soft compared to the cow. So they will not sink, they will not give much pressure to the sand. As a result, a camel can walk easily on the sand. The feet are not sinking on the sand. Hence, a camel is used for traveling in the desert. That means on the sand. All right. Now, the next example that we see is here. For the skiers, they never walk on the snow, all right, on the snow simply by their feet. Instead, they use skis, and the skis are long, all right, they are long, and when they are long, it makes the area of contact to be more compared to the area of contact of the feet only. So when the area of contact is more, then you are giving less pressure to the snow. This reduces the risk of causing avalanches whenever you do skiing on the snow. More area of contact, less pressure. The next example is on the foundation of a building. Now remember, children, the building stands on the foundation on which it is built. So to make the foundation of the building to be firm, you need to have wide and firm foundation. How do they do it? They make nets like this with iron rods, okay? The net of iron rods will be placed deep inside of the standing rod. So by making the broad net like this, you are making the area of contact of a pillar with the ground to be broad, and this net will be attached to the standing rods. As a result, you will find this standing rod will have a broad base, resulting in more area of contact with the ground. Less pressure will be given by the pillar. So if each and every pillar is made like this, then you will have a strong foundation of the building. The next example is a railway track. In the railway track, if we have only these two, alright, if we have only these rails, then these rails, because of the pressure of the running train, they will be sinking in. So in order to make the area of contact to be more, we make the wooden slippers. By making the wooden slippers within short range from one another, you are making the area of contact of these rails to the ground to be more. So by spreading these wooden slippers, we make the railway track to have huge area of contact with the ground, resulting in the rails not sinking in the railway track, so the train can run easily on these tracks. So these are the few examples of increase in area decreases the pressure. Then we go to liquid pressure. What is liquid pressure? Liquid also has pressure just like solids and gases, alright? So the pressure exerted by the liquid in its container in which it is kept is known as liquid pressure. This is liquid pressure. Liquid exerts pressure in all directions. Okay, very important. The pressure exerted by a liquid in its container in which it is kept is known as liquid pressure. Liquid exerts pressure in all directions. Okay, in the case of a liquid cannot stand on its own. It has to be kept in a container. And a liquid, whenever you keep it in a container, will exert pressure in all directions in the container. That pressure exerted by the liquid on the container in which it is kept is known as liquid pressure. Unlike solid, liquid exerts pressure in all directions. Solids usually exert only at the bottom, but liquids exert pressure in all directions. Factors affecting liquid pressure. The pressure at a point in a liquid depends on the following two factors. Okay? Number one, the height of the liquid column. And this height of the liquid column, usually it's measured from the open surface. Alright? Liquid pressure increases with the height of the liquid column above the point. So if you have the height, if you have the surface here, if you measure the height, more will be this height from the surface, more will be the pressure. Then two, the density of the liquid. Liquid pressure increases with the increase in the density of the liquid. More is the density of the liquid, more will be the pressure exerted by the liquid. Hence, not all liquids will have the same pressure. Water will exert pressure on its container differently than that of glycerine, and glycerine is different from mercury and so on. Okay, it increases with the increase in the density. That means higher density will exert more pressure. Now, this height of the liquid column has a very profound application in the wall of a dam. You will find whenever a dam is to be constructed, the bottom will have a broad and thick wall, all right, than the upper portion. So if you look at the dam, you will find the top one is made thinner, whereas the base is made thicker and broad. Why is it so? The reason is this. Remember, if you make a dam, then the water will be accumulating in this area, all right? So higher will be the height of the liquid, higher will be the height of the liquid, then you will find the pressure will be more. So if water is accumulating here, then at the bottom, because of the height from the surface, all right, the pressure will be more. In order to make the wall to withstand this increasing pressure at the bottom, the wall of a dam is made broad and thicker at the bottom. Then we go to the next type of pressure, that is atmospheric pressure. All right, we need to know what is atmosphere. The envelope of air around the earth up to a height of 200 kilometers is known as atmosphere. Okay, so basically atmosphere is consisting of air, and air that envelopes the earth all around up to a height of 200 kilometers measuring from the earth's surface. All right, we have air and air and air all around the earth. So that envelope of air around the earth up to a height of 200 kilometers is known as atmosphere. Atmospheric pressure. Remember, we are talking about air here. So when we talk about air, we usually take it for granted that air has no thrust. But remember, children, air has thrust. And let me tell you something. We have seen that 1 atmosphere is equal to 1.013 into 10 to the power 5 Pascal. Okay? This is not a small pressure at all. You know, this is not a small pressure. This is equivalent to having one big adult elephant on your head. It's a huge, huge pressure. All right. So if we take the thrust on unit area of the Earth's surface due to the column of air, this is called the atmospheric pressure. So atmospheric pressure at sea level is equal to 76 centimeter of mercury. If you take it in millimeter, that will be equal to 760 millimeter of mercury column. And this is the one that we call 1 atmosphere. 76 centimeter of mercury or 760 millimeter of mercury is the one that we call 1 atmosphere. And 1 atmosphere is equal to 1.013 into 10 to the power 5 Pascal. Okay. Interestingly, the atmospheric pressure is highest near the surface of the Earth. As we go higher and higher with height or altitude, we find that atmospheric pressure decreases. So atmospheric pressure decreases as the altitude or the height increases. So if you go to high mountains, you will find the air will become thinner and thinner and thinner as the height is higher and higher. Here we have some applications of the action of atmospheric pressure, which are given in your textbook, but there are some which I could not get any diagrams. Okay, the first one that is given in your textbook is we suck a drink with a straw. Okay, we suck the drink with a straw. Why do we do that? And how do we do it? Okay, now remember, inside a straw, before you suck a drink, there will be air. And air, whether it will be in a high column or whether it is filled in a small area like a straw, air will always exert pressure, which is similar to the atmospheric pressure that we have. So when air is filled inside a straw, it will never allow anything to come up inside a straw because air occupies the space and exerts the pressure. Now, if you simply dip one end of the straw inside the drink will never come automatically inside the straw. So what do you have to do? You'll have to suck first. Initially, when you suck, you'll find the drink is not coming immediately. Why is it so? Because when you first suck, you are sucking the air from inside the straw. This air will now enter your mouth, it will go into your lungs. And once you suck out the air from inside the straw, then there will be less pressure inside the straw. But atmospheric pressure is acting on the surface of this drink. So this atmospheric pressure now will push the drink to enter into the straw, which will come to your mouth. In fact, you are sucking the air only. It's the atmospheric pressure that helps the drink to come into your mouth through the straw. Why? Because when you suck the air, less pressure here, more pressure here. So the more atmospheric pressure will push the drink into the straw, which has less pressure, which forces the drink to come into your mouth. The next example is about the balloons. Now, I'm not talking about flying of a balloon, which I did last time. But here, what I'm going to explain to you is before you push the air into the balloon, you'll find the balloon is collapsing. It does not show you the shape. You will not find it bulging out like this. Okay, you will not find it bulging out like this, but it's flat and there's no shape in it. But then when you pump air inside, it bulges out. Why is it bulging out? The reason is when air enters into the balloon, it takes the space inside the balloon. Okay? And then as soon as air enters, it also exerts the pressure on the balloon, which makes the balloon to have the shape and then to swell up like this, bulging out. So the air, be it inside a balloon, be it outside, once it is present inside a body, it will exert pressure, and exerting pressure helps the balloon to take the shape that you see. All right? The next example that we see is in filling a fountain pen with ink. Okay? When you want to fill ink inside a fountain pen, you will find by simply dipping the nib inside the ink will never come inside the tube. What you have to do first, you will have to squeeze this rubber tube. Okay? Why do you have to squeeze? Because when ink is empty, air will occupy the space inside. When air is present, it exerts pressure, so ink can never come inside on its own. So by squeezing, you are pushing away the air from the inside of the rubber tube, which you will see will come out as bubbles on the surface of the ink. So when air is released from the inside of the rubber tube, then you'll find that ink will get into the rubber tube and fill it. All right? And how is it so? Because when this inside area is reduced in pressure, then atmospheric pressure is acting on the surface of the ink. It will force the ink to get into the area which has less pressure. That means the inside of the rubber tube. The next application is in drawing water by water pump. Okay? When you draw water in a water pump, what do? You are making the inside of this tube. You'll have to push out the air from the inside of the tube. Then the atmospheric pressure which acts on the surface of water will force the water to come up, and then water will come from the tap. The same is also applied in filling a syringe with a liquid that is needed. Okay? Now, inside a syringe, you will find there is a rubber tube as well. You need to squeeze the air from the inside of the rubber tube first in order to free it from the pressure exerted by air. And if air is present, it will exert pressure. Liquid can never get in. All right? But once you drive away, you make the air to be free. You push it, and this will go to the surface of the liquid here. Then low pressure will be inside the tube, which forces the liquid to get inside it. Okay, so these are few examples that here we have some more. This is known as a rubber sucker. Okay, a rubber sucker is used as a hook for hanging something. All right, now you'll find here is a wall. A rubber sucker is not at all fixed. All right, it's not at all fixed. You simply have to attach it to the wall. All right, so what do we have to do in order that this rubber sucker will stay on the wall? You'll see this portion is somewhat crooked. All right, it bends. Now air will occupy this space if it is not removed. So in order to fix a rubber sucker, what you have to do is you'll have to fix it very hard and very fast. Why do we do that? By pressing it very hard, you drive away the air from this area. Doing it very fast will make the air from the outside not to get inside, so that there will be no air here. So it will be a partial vacuum, not totally a vacuum, but it will be a partial vacuum where we will have lower air pressure. But the atmospheric pressure, which is higher, will now be acting from the outside. So more pressure from the outside, less pressure from the inside, so a rubber sucker can stay on the wall without fixing it with any material. The next application is in a lizard. The feet of a lizard is more or less like a rubber sucker. Now whenever a lizard walks, it will press the feet very hard to the wall, making this underside of the feet to be a partial vacuum. All right, and atmospheric pressure which acts from the outside will be stronger, making the feet to stay in anything that a lizard will be crawling. So you'll find lizards anywhere, everywhere, including the glazed wall, because it can crawl on a vertical glazed wall based on this principle. The next application is the dress or the costume that an astronaut or mountaineering people, all right, they will be wearing. They cannot go in ordinary clothes that we are wearing. You'll find them to be wearing special suits. Why do they have to do so? Remember, I had mentioned just now that as we go higher with height, okay, the air will become thinner, and as the air will become thinner, less dense, then the pressure will also be reduced. All right. Now, as you go higher and higher, the pressure of the atmosphere will be reduced. When the pressure of the atmosphere is reduced, then we have inside us another pressure which we call the blood pressure. Now, usually when you have the blood pressure inside to be more than the atmospheric pressure, then there will be some effects on the body. To protect the body from that, you need to have special suits. So these are the suits which mountaineers will wear, and the astronauts also will need special suits so that they can protect their bodies from the effect of more blood pressure and less atmospheric pressure from outside. This is a protective suit. Okay. And another example that we have is nose bleeding is a common phenomenon at high altitude. Why is nose bleeding so common at high altitude? The reason is this. Remember, just now I had mentioned to you, atmospheric pressure decreases as we go higher and higher with altitude. So as you go higher and higher with altitude, atmospheric pressure, which is slightly higher than the blood pressure, which is slightly higher than the atmospheric pressure, okay, then when you go to altitude, the difference will be more. I'll just give you an example to be clear. Suppose now you are in Delhi, which is at a much lower altitude, and you are climbing the Himalayas. In Delhi, when you are at a lower altitude, your blood pressure is slightly higher than the atmospheric pressure, okay? But when you climb the Himalayas, as you go higher and higher with the altitude, you'll find that the air will become thinner and thinner and thinner. So atmospheric pressure will become less and less and less. A point will come when the difference between your blood pressure and the atmospheric pressure is so much that the body now will try to react. There is a valve at the junction of the nose and the eyes. Okay, there is a valve. This valve is the first one to open up when there is a difference between blood pressure and atmospheric pressure, when there is more on the inside of your body and less from the outside. It opens up, and when it opens up, blood will start flowing, and the first part of the body that it will show will be the nose. Hence, nose bleeding is common at high altitude.